Up to now, we've been dealing with just calculating Kas given equilibrium concentrations, but we can actually, given a Ka, calculate the equilibrium concentrations of species in solution. I think this is best illustrated by just doing an example. So let's say we've got this one here, calculate the amount of the concentration of HCNO, H3O plus and CNO minus given HCNO, and we've got an initial concentration here and a Ka value is given as well. So what we'll do is we will take our HCNO and we'll split it up into H plus and CNO minus. Now remember here I could also have done this. And that is made at H3O plus and CNO minus. Either way is okay. I'm going to stick with the top one just because it's a little bit easier for me to work with. But understand that H plus and H3O plus are going to be the same thing, and I've used them interchangeably here. See, I'm after H3O plus, but I'm going to calculate H plus. It's going to be the same. Alright, so going back to our problem, we've got initial concentrations, we've got equilibrium concentrations. This is going to start out at 0.184. This will be 0, this will be 0. At equilibrium, this will be 0.184 minus some amount z. This will go up by z, this will go up by z. So just like we were dealing with the other problems, you'll find that the HCNO4 will go down by a certain amount and these will go up by the same amount, because whatever we lose of this we gain of these two, and we gain them in the same amounts. Right, so now we can move on. We can write our Ka expression down. So the Ka is going to equal concentration of H plus, concentration of CNO minus, over HCNO. Now what I'm going to do is I'm going to plug my known values in there. I was given the Ka. Oops. And we've got z squared on top. That's z times z. And down here we'll have 0.184 minus z. Now if you look closely, you'll see that this could actually be solved, and it would have to be solved using a very nasty quadratic equation. I'd actually like to try and avoid that, and I can if I make a certain assumption. And that assumption is as follows. If I assume that we are dealing with a weak acid, then I can allow this assumption to be used. I can say assume 0.184 minus z is approximately equal to 0.184. Alright, let's say, so what do we mean by that? Okay, a weak acid by definition means we're getting a very small amount of H+. If we're getting a very small amount of H+, it means this isn't going to be breaking up very much. Now how can I know it's a weak acid? I can do that by looking at the Ka value. In a previous mini lecture I discussed the relevance of Ka and its relationship to concentration of H+ and the strength of an acid. And one of the things I talked about, I said that there was a dividing line between strong and weak acids when you look at the Ka. And you could say that if the Ka is less than about 10 to the negative 4, then you can try and make the assumption that it is a weak acid. If it's greater than 10 to the negative 4, then maybe you won't be able to use that assumption. Alright, well let's talk about what this assumption means. Again, if we're saying that Z is small, we're saying it's small relative to 0.184. Alright, let me give you an example of that sort of more in picture form. And what I'm talking about is this. If you've got a hole, and then make it a circle like this, and you just take a very small part of that circle, you're still going to have most of the circle there. And what I'm saying is this part of the circle is small relative to the larger part of the circle. And you can almost is that this part with the little bit taken out is almost equal to the whole thing with nothing taken out. And that's really the essence of the assumption that we're making here. And it is a valid assumption because we are dealing here with a weak acid. And the reason we know that is because we got 3.46 times 10 to the negative 4, so we're in that realm of being able to attempt to make that assumption. Alright, so that's where we're up to in the problem. So I've gone that far. I'm making the assumption that 0.184 minus Z is approximately equal to 0.184. Now, if I do that, I'll go back to what I had before. So I make my assumption. And I'm going to transfer that in here. Alright, so you can see what I've done is I've replaced 0.184 minus Z with 0.184, and my argument is that this is so small compared to this that I may as well just be talking about 0.184. Now, in a little bit I will be validating that assumption, and I'll show you how to do that in a second. But now I can actually go ahead and calculate Z, and the mechanics of that involve just multiplying 3.46 times 10 to the negative 4 times 0.184, and then taking the square root of that entire number. And that's going to give me a value of 0.00798 molar. Alright, so that's our value of Z right there. The next thing we're going to do is I'm going to validate that assumption. This was the assumption I made, that 0.184 is the 0.184 minus Z is approximately equal to 0.184. So how do I validate it? Well, what I do, going back to my previous example here, I can validate the assumption I made here by saying, well, what if we take the area of the slither and divide it by the area of the hole and see what kind of percentage we get. And if it's a small slither, then this will be a very small percent. But what is a small percent? Well, according to us, and this will be our guideline here, less than 5%. So as long as this slither is less than 5% of the whole, then we're going to say that this is a valid assumption to make. Now we're going to do the same thing over here with ours. Now we've got our z value. So what we're going to do is we're going to take z and divide it by the initial concentration of HCNO. And we'll multiply that by 100%. That'll give us a percentage. So it'll be 0.00798 divided by 0.184 multiplied by 100%. And this comes up to 4.33%. So what this means is that 0.00798 is actually about 4.33% of 0.184. Since this is less than 5%, and that's our guideline, that's our breaking point, and since this is less than 5%, then we're going to say that the 0.184 minus z being approximately equal to 0.184 was a valid assumption. So understand this. Let's say it had come out to greater than 5%. If it was greater than 5%, what that would indicate is that this would not have been a valid assumption. And my only choice would have been to go back and solve that nasty quadratic equation that I had earlier. So, if it turns out that the z value is less than 5% of the entire thing, then we're going to say that this was a valid assumption and we can continue on with our problem. Alright, to complete the problem, we can go back to our initial table. Which is this one up here. I'll go ahead and rewrite that so you can actually see it all. And I'll just put in the equilibrium concentrations, that's what we're interested in. And we 0.184 minus z. And z and z. So the concentration of HCNO at equilibrium will be 0.184 minus z, which equals 0.184 minus 0.00798, which equals 0.176. Now when you're looking at the significant figures here, it's going to be based on the number of decimal places. We've got 3 decimal places here and 5 here in z. So this is going to make this 3 decimal places, will be 0.176 molar. That'll be our final concentration of HCNO. The concentration of CNO minus and the concentration of H plus will both be the same, and that will be 0.00798 because they both equal Z. Alright, so that's how we handle that kind of problem.